Hello, Weather and Climate. This is the second video in the section on heating. This is the third module, Unit 1, Module 3. And just a quick review, I wanted to remind you, we talked about the relationship between latitude and sun angles. So low latitudes near the equator tend to have much higher sun angles, as shown in this example. What does that cause? Why do they get more energy? Because higher sun angles are more concentrated and higher sun angles pass through less atmosphere, as you can see here. As I go toward higher latitudes, in this case, like toward the North Pole, what do we find out? Sun angles are lower. Why does that give less energy? Because lower sun angles are more spread out, and lower sun angles, as you can see here, pass through more atmosphere. So that's a very fundamental thing to understand when we want to try to understand distribution of energy on Earth. So I'm going to enable my pointer here. So our main goal here is to take a look at seasons, and you really need to rely on the visuals, and you'll probably need to rely on some of the video extras to make sure you understand this concept. Why do we have seasons? Now, first of all, remember we've got notes at our disposal. We give names to seasons: winter, spring, summer, fall. Turns out that we can use an astronomical definition or a climatological definition. So I just want to make you aware of that. And this little table straight from your book. So many people, when they talk about the first day of spring or the first day of summer, they will be using the astronomical definition. So first day of summer, June 21st, the June solstice. And again, we'll talk about what that means. But frankly, it's already pretty darn warm by the time we get to June. And so personally, I often revert to the climatological definition, which is just months of the year broken into three chunks. So summer generally is June, July, August. And what do we find during June, July, August? In the Northern Hemisphere, in and around Northern California, we find that hours and angles are high. Hours of sunshine per day and angles of sun in the sky are higher. What about winter? So the astronomical definition would be December 21st, it starts, and then it ends on March 21st, approximately. But the climatological definition, when is it really coldest? December, January, February. Why? Because generally at that time of year, the hours of sunshine per day are at their lowest. The angles of sun in the sky are at their lowest, low angles and hours. So again, I'm just trying to give you some sound bites to help get your brain used to this and try to simplify it. It's all about hours and angles. So just remember your astronomical versus your climatological seasons. So again, before we get farther into seasons, we have to take a look at Earth moving through space and make sure we understand the difference between a couple of basic concepts, being, in this case, rotation and revolution. Okay, so, and here's a graphic that shows the climatological seasons. So you can see this, take a look at this. But rotation is Earth spinning on its axis. And as hopefully you know, this happens once per day. One rotation per day, that's what defines a day, one full spin. And we'll talk more about that. Revolution is the journey around the sun, the orbit, if you will. And it's doing both at the same time. It's both rotating on its axis once per day, and it's revolving around the sun once per year. So really, to understand these dynamics, you have to understand both rotation and revolution. And 1 year is 365 days. It's actually a little bit more. We might get into that briefly. But again, make sure you're understanding the difference between rotation, is the spinning on the axis once per day, and revolution, which is the orbiting or the journey around the sun, which it does one full orbit once per year. Now, that doesn't necessarily help us understand seasons. Let me say that about revolution, it's commonly misunderstood. You could probably find a lot of people in your family, and maybe you believe this. It's okay. We're here to learn. But many people believe that we have summer, for instance, because Earth gets closest to the sun during the course of the year. And when it's closest, that gives us summer. It's absolutely, positively untrue. There is no truth to that whatsoever. And we'll explain why. It seems so logical. Here's the deal: is the Earth does get closer to the sun during a certain time of year and farther from the sun during a certain time of year. And those concepts, it's explained in your notes, you need to understand, are called perihelion and aphelion. So you see that in your notes. And let me show you what I'm talking about here. Here's a graphic which shows this. It's a very subtle difference. It's a fairly small amount. In this case, a few million kilometers, which, seems like a lot, but percentage-wise, it's only a few percent difference. But at what time of year are we, the entire Earth, farthest from the sun? Closest to the sun, January 3rd. We are closest on January 3rd. Well, that doesn't sound like it gives us, a nice warm summer. January is going to be cold for us. When is Earth farthest from the sun? Aphelion, right around July 4th. So this right here, this basic data should help dispel any thought that we have summer because we're closer, we have winter because we're farther. Okay. In fact, we are closest on January 3rd, perihelion. We are farthest on July 4th, aphelion. So make sure you're aware of that. Here's the fundamental deal. And in this graphic, it shows that Earth is tilted on its axis. Now, the technical phrase is that Earth is tilted 23.5 degrees from a perpendicular to the plane of the ecliptic. And that is really a mouthful. That's wordy, that's confusing. I have this little bouncy ball, you can see it. And if there was no tilt, the North Pole would poke out like that, the imaginary North Pole. Earth spinning on its axis. But what we find is that, in fact, there is a tilt, and it is a tilt of 23.5 degrees compared to straight up. So if you see in my little example, that would be straight up, but you see the little toothpick is now creating the angle, 23.5 degrees. So that's what we need to remember, 23.5 degrees. It changes very slightly over a long period of time. We'll talk about that later. You just need to remember for now, 23.5 degrees. And the North Pole is always tilted toward the north. That will also change if we wait around long enough. But for now, we stick to that. It's tilted 23.5 degrees and it's pointed toward the north. It always stays pointed in the same direction. That's incredibly important to remember. And look at the graphic here. It shows that. There's the North Pole right there. It's tilted. Over here, it's tilted at the same angle. Over here, it's tilted at the same angle. And the same over here. So during the course of the year, the relationship between the Earth and the sun is what changes, the relationship between the Earth and the sun. So let me jump to this next graphic, which is pretty good. There's no easy way to show this. I will again tell you in the video extras, you're going to get some good graphics that'll help this soak in. But let me say that when you combine this revolution and the tilt, that is fundamentally how we understand seasons. So I'm not going to read all of this word for word here. You're going to have to go in and digest some of this, but I'm going to try to give an overview of what's going on. So ultimately, the best way to think about seasons is whether one of the hemispheres, remember, hemisphere is half of a sphere. So we talk about all of the part of the Earth north of the equator, that would be northern hemisphere. That's where Sacramento is, and the whole United States is in the northern hemisphere. And then all of the area south of the equator. So in this graphic, this would all be south of the equator. That's the southern hemisphere. So these are terms that you need to be familiar with. Seasons are really about whether your hemisphere is tilted away from the sun or toward the sun at a certain time of year. So over here, this is referred to as a solstice. A solstice is when Earth reaches its most extreme tilt either away or toward the sun. The December solstice is when the northern hemisphere is tilted most directly away from the sun. Well, of course, take a look at this sphere. If the northern hemisphere is tilted away, in my example over here, the southern hemisphere has to be tilted toward. So we introduce another concept, is that the northern hemisphere and the southern hemisphere always have their seasons at opposite times of year. When the northern hemisphere, when we're having summer, they're having winter, and vice versa. So it is all about whether you're tilted toward or away from the sun. That's the most basic way to think about it. When we get over to the June solstice in the northern hemisphere, we are tilted toward the sun. The southern hemisphere is tilted away from the sun. Really key thing to understand. On the equinoxes, it turns out even though the tilt is still there, the hemisphere, north or south, is neither tilted toward or away from the sun. It's kind of tilted toward the side, which means that on the equinoxes, really everything is equal. The northern and southern hemisphere get about the same amount of energy from the sun. So to add in something we already talked about, what is it actually that gives us, I'll go over here to the June solstice, what is it that gives the northern hemisphere summer? Just because we're tilted toward the sun, what does that mean? Well, it turns out that means that our angles and hours are at their highest. So remember, I said we talked about angles and hours just with regard to latitude, but also it's an issue of time of year, angles and hours. So why do we have summer? Because we're tilted most directly toward the sun. What does that cause? That causes our angles of sun in the sky to be highest of the year, and that causes our hours of sunshine per day to be highest. So summer is really all about high angles and hours because we're tilted toward the sun. Winter is all about low angles and hours because we're tilted away from the sun. That is the best way to think about this. So let that soak in. That's critically important. Now, I want to add one more detail as you look through this. Again, you can read through this, but I want you to, and these dates are approximate. So a solstice, remember, is when the tilt either toward or away is most extreme. An equinox is where the tilt is neither toward nor away from the sun. And you see, again, these dates are approximate. I just say the 21st of each of these months. It changes slightly every year. But I'm going to add one more important concept, and that is the declination. The declination you see right here, my little definition, is the latitude of the vertical or direct ray. The latitude where the sun is directly overhead, and this has a direct relationship to season. So on the December solstice, the sun passes directly overhead at 23.5 south, called the Tropic of Capricorn. On an equinox, what do we know? The sun passes directly overhead on that day at the equator. That's why an equinox is called an equinox. Equinox, equator. On the June solstice, the sun is passing directly overhead at 23.5 north, called the Tropic of Cancer. And again, at the September equinox, it's doing the same thing as it did during the March equinox. So the declination during the course of the year is what changes. The direct ray will never get farther north than 23.5 north. It will never get farther south than 23.5 south, but wherever that direct ray is, whatever the declination is, that's an indication that that part of the world is getting the highest angles and hours of the year. So if the declination is in your hemisphere, your angles and hours are going to be higher. If the declination is in the opposite hemisphere, their hours and angles are going to be higher. Yours are going to be lower. So I'm going to let you read and digest this information here. It compares the northern and the southern hemisphere, but I want to show you one more little slideshow. So let me take this, and this is approximately in my little slideshow the March equinox. So we have the tilt, the axis is tilted 23.5 degrees toward the north. And remember, the tilt never changes. The amount of tilt never changes unless we wait around thousands of years. It's the relationship between the Earth and the sun which changes. So March, April, May, June. And what's happening this whole time, right about June 21st, what do we know is the direct ray, the sun is directly overhead. That would be called a 90-degree angle at the 23.5 degrees north. That's this little green line shown in the graphic. And then as we move from there, the declination now moves further south. It's kind of harder to see on this. August, September 21st, now the declination is hitting directly at the equator. September, October, November, December 21st, what do we now know? The declination is hitting at 23.5 south. It will never get further south. And it's kind of hard to see in this graphic. One of the things I'm not going to dwell on a lot, but remember, when angles of sunshine go down, hours of sunshine also go down. And there are some extremes here you may have heard. In this case, this red circle is called the Arctic Circle. It's 66.5 degrees north. On this day here, you can see any place inside the Arctic Circle, which is mostly frozen ocean, the sun doesn't even come up, doesn't even come into the sky. And depending on how far north of the equator you are, you might get 1 or 2 days of darkness, complete darkness. You might get a week. If you go farther north, you might get a month or 2 months. And if you are at the North Pole, the sun sets on September 21st, and it does not rise again until about March 21st. 6 months, the sun stays out of the sky. And then for 6 months, it stays in the sky if you are at the North Pole. So again, you have to spend some time looking at this. And we go December, January, February, March, right about March 21st. What happens again? The direct ray of the sun is hitting at the equator. Let me go backward here. So here was approximately March 21st. If you're at the North Pole in this little example, the sun just came into the sky. And take a look, keep your eye on the North Pole here. The sun never goes down. Okay, so June 21st, all of this area inside the North Pole, inside the Arctic Circle, never tilts away from the sun, 24 hours per day, in some cases for 6 months on end, if you are actually at the North Pole. Same thing is true for the South Pole, except at the opposite time of year. So, long story short, you have to spend some time with this. You have to sit with this, think about it, watch the YouTube videos I give you to digest this concept. Let me go back for a second. Again, this graphic shows pretty well, and it talks about, the sun vertical, sun vertical at the equator, sun vertical at latitude 23.5 degrees south, Tropic of Capricorn. They're talking about what I call the declination. In your notes, I called that the declination. Okay, so you need to be familiar with that term. But let me just march you through. So they have individual graphics which kind of show this, but it kind of makes it look like the tilt is changing. Remember, the tilt doesn't change. But in June, if the sun's coming from here, it is highest at 23.5 degrees south. If you were standing right there, the sun would be directly over your head. It would rise in the east, it would go directly over your head, and it would set in the west. December, again, it's the opposite. So the sun would be directly overhead at 23.5 degrees south of the equator. Take a look in the graphic. Everything north of this line never goes into the sunlight. Everything south of this line never goes into the darkness. That's the Arctic Circle and the Antarctic Circle. And then what do the equinoxes look like? It makes it appear as though there's no tilt. The tilt doesn't have any effect. The tilt is still happening, but it doesn't have any effect. The area of light and dark slice right through the North and South Pole on an equinox. Where is the sun directly overhead? At the equator. So the March equinox and the September equinox essentially don't look much different. So what is the net effect again for a place like Sacramento? June 21st, the sun is at its highest in the sky, and we have the highest hours of sunshine per day. And then on an equinox, it's lower in the sky and we have medium hours of sunshine per day. And then on the December solstice, it is lowest in the sky and there are the lowest hours and minutes per day. So low angles and hours in this case, medium angles and hours in this case, and highest angles and hours in this case. Okay? Now, one last thing. I've given you, in this case, the answers to a set of problems that I'm going to ask you to work through. On the next page, here you have all these answers, and it presents the problem of how you would calculate a sun angle. In other words, how high did the sun get in the sky, a maximum sun angle? Because every day, of course, it starts at 0 when it rises, it ends at 0 when it rises. We measure angles from the horizon, from the distance. Directly over your head would be a 90-degree angle. Straight out in front of you, setting or rising, would be a 0-degree sun angle. So how do you figure that out? Well, if you know your latitude, okay, and of course Sacramento's latitude doesn't change, and you know the declination, I gave you the declination, where is the sun directly overhead? You simply compare the latitude to the declination. You take the difference, how many degrees apart are they? And that's a tough one. Notice that in this case, the difference between being at 23.5 north and all the way down at 23.5 south, you have to add those numbers. So here's the difference, is 62. In the case of the March equinox, what's the difference between these two numbers? Well, the difference between 0 and any number is that number. For the June solstice, if our latitude hasn't changed, 38.5 north, where is the sun? It's fairly close at 23.5 north. Just think of a number line, okay? If you're on the same side of the number line, you simply subtract, okay? So that's a very small difference. Well, if we know where the sun is directly overhead and we know where we are, we just take that difference, we subtract it from 90 to get our sun angle. So that's what these numbers are. Take the difference, subtract it from 90, and you get your maximum sun angle for that day. So how did we get this? 90 minus 62 equals 28. 90 minus 38.5 equals 51.5. 98 minus 15 equals 75. So what's the net result? For Sacramento, what do we see? We see numbers that are fairly logical. In the December solstice, the sun angle is at its lowest for the year. On the equinoxes, it's kind of halfway between. And finally, on the June solstice, it is at its highest of the year. So you should spend a little bit of time thinking about this concept. Let me also say that this concept of horizon is going to become more important, but it basically compares your location to where the sun is hitting directly. So if you think about it, Sacramento is way up here at 38.5 degrees north of the equator. And the sun, the declination of the sun changes during the year, but it never gets farther north than 23.5 north or farther south than 23.5 south, okay? So in other words, we're way up here. The sun is always somewhere down here. Well, think about it. Where is the sun in relation to us? The sun, this is the sun. The sun is always south of us. It always passes through the southern sky. If you know your directions at all, if you have a window in your home that faces south, that window always gets the most sun because the sun is always passing through the southern sky. In the summer, it might pass really high through the southern sky. In the winter, it might pass really low through the southern sky. But the point is, it's always in the southern sky. So that is how you figure out horizon. If I were ever to ask you to figure out horizon, just take a look at the latitude that you're talking about. And again, it's really easy for Sacramento. If we compare any of these times of year, the sun is always hitting south of our location. That's why the horizon is south. So that is a mouthful. This is a pretty substantial set of related concepts that you need to spend some time on. And again, I highly recommend the video extras for this section. So thank you for your valuable time, and yeah, look for the next video.